everybody, welcome back. I wanted to do a quick little tutorial on using basic exponential growth models in Stata with kind of the most unfortunate and obvious example of an exponentially growing time series, which is the US cumulative caseload of coronavirus or COVID-19. So the disclaimer, I'm not a medical doctor, I'm not an epidemiologist, just wanted to do an example of, again, basic exponential growth modeling. So this is primarily aimed at introductory econometric students, people wanting to play with this type of data in Stata, or if you're kind of your first time running through some time series models. So the plan here will take a look at the data, and as far as the data source, I'll link to where I found this data in an updated spreadsheet. I didn't do any fancy web scraping or anything like that. Lots of different sources out there for this type of data. So we'll take a look at that. We'll talk very briefly about kind of the math behind an exponential growth model. Then we'll run a couple regressions in Stata to get the parameters that best fit that growth in cases that we actually see. And then we can use that set of parameters to make some out-of-sample predictions. Okay. So as far as the data is concerned, if we bring up the data browser, again, I didn't do anything fancy here, so we could turn this time series indicator into a date variable. It'll make your graphs look a lot nicer. I'll link to a video on how to do that. I'm just counting the days, right? So when you actually look at the calendar, day 1 in the sample that I have here is January 22nd, and it takes us all the way up through yesterday from when I'm filming this, which is March 26th. So we go from one case to 83,000 in an increasingly accelerated fashion, right? So our first step, again, since we're using this as a time series data set, before we can use the time series operators, we have to declare our data set as a time series. So we go tsset days, and now we can use that tsline command. And the name of the variable here is just US. So this is, again, tracking cumulative cases in the United States. And we get a depressing graph like this, right? So for a long time, not much growth, and then the exponential growth really kicks in. And again, we're up to over 80,000 cases now. So now the question is, how could we generate a regression model that can track this sort of growth rate to give us parameters that we could use to generate, again, out-of-sample predictions? Well, if we recall, when we talk about an exponential growth model, right, if our dependent variable is y sub t, we can model it as an initial value, call it a, times e to the power delta t, where t is representing the passage of time, in this case day by day, and the delta term is our growth factor. So when that delta term is positive, we're going to see that growth over time. The larger the value of delta, the faster that growth occurs. So if we know what a is and we know what delta is, we can make a prediction for time t plus 1, t plus 2 for what that outcome is going to be. The trick is, how do we estimate these parameters in a regression model, right? So if you recall, kind of the first core assumption of using an ordinary least squares regression is that it has to be linear in parameters, right? So the intercept and the slope parameters have to enter into the equation in a linear fashion, not as part of an exponent like we see in the delta term here. So a good trick here to linearize this growth model is to use a log transformation, right? So if we take the log, the natural log of our dependent variable, yt, We're taking the log of the expression on the right-hand side. So we're doing two things, right? We're taking the log of a product, a times e to the power delta t. So the log of a product turns into the sum of the logs. So it's log of a, that initial value, plus the log of the exponential e to the power delta t, which is just delta t. So now we have a linear function, right, that we can estimate with OLS. And from that, we can go back and recover what that initial value is, the a term, and we'll have a direct estimate, a delta hat, for that exponential growth factor. And once we have that, we can recover the predicted values of y itself, and again, in our example, the number of cases, by taking the exponential of the fitted log value. And that'll be our model's prediction. Okay? So, with all that said, let's run some regressions, right? So let's estimate that log function first. So in Stata, we can't insert a log transformation within a regression command. We have to go ahead and generate the variable first. So we can use the generate statement, and we'll call this just log underscore us equals log log us. So that's taking the natural log of every observation of our variable, our case load variable. And we will note if we plot that out, again with the tsLine function, we've now created a much more linear function. But remember, when that log is increasing linearly, the underlying data is increasing exponentially, right? But this is now going to be what we're trying to predict in our linear model. Okay? And from a regression standpoint, the x variable in our regression is simply time, right? As each day passes, how does that predict the impact on our log caseload? So let's go ahead and estimate this log model. So we'll just use the OLS regression command, regress log us as a function of days, right? The number of time periods that pass. And now we have an estimated delta, right? Our delta hat here is the coefficient of 0.156. And then this term, the intercept, is actually our estimated log of a, the log of that initial value. So if we use the predict command here, this is going to give us our predicted log value, right? So let's just go ahead and do that. So this is our y hat from this log linearized model. So log us hat. And then we can get the visual here, the kind of the initial fit of our model, by setting the actual values, the logged caseload versus our predicted logged caseload. And let's see how we did. Well, okay. Our fitted values, our perfect linear trend, and the actual values kind of cycle about that. So not too bad. But it's hard to tell exactly what's happening there because, again, those are in log values. So let's use this expression down on the bottom to recover the actual predicted values. So we're going to take the exponential of those log fitted values to recover the predictions of the actual caseload. So we use this with the generate statement, and we'll call this us hat 1, which will be the exponential of the log prediction. Okay. And now we can put this side by side with the actual caseload, the US, and our fitted values, again, recovered from that exponential transformation. And what we see here is we did not do a great job, right? We seem to be under predicting the actual growth rate that we are seeing in the data, right? And I think what's happening here, if we go back and look at the raw data, is that for the first 30 observations or so, we see a lot of cases like this, right, where our reported caseload was stuck, say, at 11 for 8 days in a row, 13 for 9 days in a row. Clearly what was happening is there was no testing going on, right? So we're underreporting, underrepresenting the true value. So I think what we can probably do is a much better job of prediction is if we bring up the sample, right? So we don't include, say, the first 25 or 30 days of reported values, because the exponential growth that's actually occurring wasn't being recorded in the data. So let's try this. Let's run our model one more time. So we're going to regress log US as a function of days if days, say, are greater than 30. So we'll drop out those first 30 observations. So now we see that growth factor, that delta hat, jumped up to a 0.26. And I'm also going to use kind of another method to generate our prediction here. So let's call this US hat 2. And instead of using the predict function, let's actually generate it by taking that exponential, right? So we're going to take the exponential of our A hat, which is the negative 5 point, and again, I'm being very low tech here, just typing it in, 5.786109 times our e to the delta t term, right? So this is going to be times exp, and then we plug in our delta hat, the 0.2610112, times days. Okay. And now let's plot these together. So the actual data, our old prediction and the new prediction. And let's see how we do. A lot better, right? So this green line is our new prediction line, and those parameters, again, once that exponential growth started to take off, we captured that in our prediction, and our model is doing a pretty good job of tracking, again, unfortunately, the exponential growth in cases. Before we get to looking at the out-of-sample prediction properties of our model, let's do this one more time using the nonlinear estimator in Stata. So nonlinear least squares uses an iterative numerical technique to get the optimum sum of squared residual minimizing set of parameters rather than solving the first order conditions, the normal equations from OLS. And what that gives us is the ability to directly estimate parameters in a nonlinear model. The characteristics in terms of inference and hypothesis testing are going to be a little bit different, but for the purposes of prediction and forecasting, this is going to be a real nice way to get where we need to go here. So the syntax in Stata is a little bit different from what we're used to. So first off, the command in L, and then we put everything in parentheses. We got to try to keep track of all the parentheses here, and we actually write out the equation. So we take our dependent variable equals, and then every parameter that we're trying to estimate, we put into curly brackets, right? So our first parameter is going to be, we'll call it A0, that's that baseline value, and that's multiplied by the exponential function of our second unknown parameter, delta, and then call it whatever you want, but whatever goes in curly brackets, that's what Stata is going to estimate. And we multiply delta by the number of days, and then we go end parenthesis for the exponential function, end parenthesis for the estimation. And let's also go ahead and restrict our sample to start at the 30th observation, again, once that exponential growth really kicked off. And here's the iterations happening right before our eyes, and hopefully right about now we get our results, right? So these are the direct estimates over the sample of the A0 hat and the delta hat and our model's prediction here, we can get straight out of that predict post-estimation command. So let's call this US hat, where are we, 3. And let's put this on our ever-expanding time series plot. So we had our first 2 cracks at it, and then our last one, and we should see those last 2 do a pretty good job. So the fitted values here, those are from the nonlinear model. Those seem to track best with the actual data. Here is the restricted sample linearization of the log model, and then here's the full sample linearization. So after all of this, we've got a pretty good idea of what these parameters are that tracks the data up to this point. And all that's left is to say, well, if this pattern continues, what is our predicted caseload in 1, 5, 10 days down the line? And again, this assumes that these parameters are constant. The whole point, of course, of social distancing and shutting down schools and shelter in place is to reduce that delta hat parameter to slow that rate of growth. So we're not factoring any of that in here, just as a data exercise. So if we go back to our data browser here, we note that the size of our data frame here only accounts for those 65 observations that we have. So if we want to create an out-of-sample forecast, we have to add some space at the bottom of our Stata data frame here. So we can use the command set obs. So the number of observations right now is 65. Let's set it up to 80. Okay, so now we've added 15 more observations. And let's now create a new days tracker, right, that goes all the way to 80, because right now all of those are empty data cells. So let's generate, call it days 2 equal to underscore little n, and that's just a counter, right? So let's browse that. Let's make sure we know what we just did. So here's our old time series tracker days. Here's our new one, days 2, and they're exactly the same, just our new one goes off into the future, right? So what we can do is just re-estimate our predicted values, right, using that days 2 as the input, and it'll track it all the way down, all the way out to the end of our sample. Right? So let's go ahead and use these parameters here to create what we'll call US hat 4, which will be our out of sample. Right? So this will be equal to the A0, so 0.005, times our exponential of our delta hat, and we'll use this 0.253, obviously I'm rounding here, times days 2. And let's browse the data first and see what we ended up with. So our new variable did a pretty good job, right? So our next prediction here is 89,000, 114,000, 148,000. Come back and check in those days to see how close we actually are. And then just look how quickly things get out of control, right? So we're 190,000 at day 69. At day 75, we're 870,000. 1.1 million at day 76. Right? So again, obviously this is assuming the parameters are constant, but it doesn't take too many days at this rate of growth to see that it's going to be ugly, right? So bringing up the TS line, let's put our out of sample versus the actual caseload here. Oop. You know what I did there? I forgot to set the time series indicator to our new value. So let's go TS set days 2 so it goes all the way out to that 80th observation. There we go. And let's go US and US hat 4. And remember that really steep line of the actual caseloads? Well, now it looks really tame and really flat because here's the prediction for the next 15 days. Right? And our scale is now in the millions. So hopefully, right, that curve will start to flatten out rather quickly and that delta hat will come down. But as far as a data exercise, I hope it was useful. Let me know if you have any questions in the comments, and I'll link some related, again, data sources and helpful videos in the description. Thank you.